complete the presentation, and he will explain the different typing of a spiking mode. So so these are my outlines. So I mainly work on the skyrmions. So basically there is different type of a skyrmion, including ferromagnetic, synthetic, antiferromagnetic, and AFM. So here I'm more focusing about the AFM skyrmion. So let's discuss about the advantage and how we can utilize to develop a model or design a reconfigurable neuromorphic system. So as you, many of in our group are aware about the skyrmions. So it is the topological spin texture. So that is stabilized by the various interactions, and it is topologically protected. So we can store the information in that in the term of some advantage, like low driving current, and the switching characteristic is very stable. So it is the create the landscape between the two states. So and here mainly maybe I can take the pointer. So yeah. So as we working on the various driving method of the skyrmion, so we thought that the static properties of the skyrmion is not much useful. Yeah, although in the nanopillar memory is useful. So basically, I am working on the dynamic properties of the skyrmion. So like we can vary the size, positions, sometimes both, to store or processing the information. So and we follow the conventional method and the some unconventional method. So there is many experimental work that drive the skyrmion using the STT or SOT mechanism. So basically, when the electrons is going to the sample, so some momentum is transferred. That means spin momentum is transferred to the spin textures, and that move along the nanotrack. And due to if there is a ferromagnetic skyrmion, so it's deviate from the original path. That means from a straight. So there is may if there is method to create the energy different across the sample. So due to this energy gradient, a skyrmion also moving. So this is the energy efficient method. So because joule heatings can be avoided. So here basically the force is acting on the skyrmion is changing the energy between two successive distance. So here I am just changing the energy of anisotropy and energy among the total energy. So that's creates the gradient. So this is the initial results that we work on the driving method of the AFM skyrmion. So basically, when the skyrmion is nucleated at a particular point, and when this associated with the anisotropy gradients, always minimized its energy, and energy minimization means bigger size of the skyrmions. So but same times we have to not create much gradient, because it if we create the much gradient, so it goes on the unstable state, and it get deformed sometimes annihilate. So as you can see in the this graph, so this is positions versus time. So when we take the highest gradients of 0. 0.2 megajoule per meter per micrometer, so its velocity and Escornion's positions is very sharp, and almost it's linear. But size of the Escornion is it feels like a non-linear, because the variation of the energy component is much as move a higher gradient. So we have also analyzed the dynamics of AFM skyrmion on the different type of gradient. So it feels like when the damping is very low, it's move around the on order of kilometers. So H, we know in the FM skyrmion is generally 100 meter per second, but due to the stray field and all these things and stabilize more, so it's around kilometer per hour. So in my case is around 500 meters per second. So in the gradient of around 2 megajoule per meter cube per micrometer. So some art, some prior art is that we have published in the IEEE Nano conference. So it is based on the DMI gradient. So and these are the results. So with the temperature analysis results, so it's feel like when the temperature is increases compared to zero, it's firing is stochasticity, showing the stochasticity varium, and it take less time to fire the neurons. And this part is taken by my student, that mean master student after.
Hi, everyone. Thank you, Ravish, for giving me the opportunity. And also, I would like to thanks all the concerned authority who has given this platform to present our preliminary going work. As already he mentioned, we are working on a reconfigurable device that can mimic the behavior of the neuron that we have. So this is our another prior work that we have taken in our consideration. Here they proposed a device which is combination of niobium oxide and electrochemical resistor. And here the niobium dioxide is working as the spiking device, which basically spikes when the threshold voltage is reached by the input. And the ECREM, which is acting as the variable resistance, it's varies its resistance whenever the resistance is varied. So based on the resistance vary, it can execute different kinds of spiking. As we can see, for different value of resistance, it can spike fast, adaptive, phasic, and bursting. So the main motivation of our work is that, as we know already, that neuron doesn't don't always fire a single spike. Based on different kinds of situation, different kinds of tasks, and different kinds of states, it's spikes various kinds of spiking behavior, like fast, phasic, and bursting, that we have considered here. So this is our proposed device that we are considering in MTJ here. The based on the implied current, the Skyrmion is nucleated, and then it's derived by the STT force, and also the anisotropic gradient is created along this nanotract, and it's acting as the leaky character behavior. So that's why it's moving backward. And these two types of uh, force is basically working in that skyrmion. Once that skyrmion moves in that MTJ, so basically it reaches at its end, and then this its device basically spikes. So this is the main analogy or concept as this device working. And we have found or observed few results also, that we have already optimized the input pulse, both the magnitude and the width, based on what we can get the fast spiking. And then also, if we goes to the next, uh, if you based on which type of input pulse, we can get the phasic type of spiking behavior, which is mainly it has initial spikes for sometimes, and then for the rest of the times it goes silent, so there is no spikes at all. So it can be controlled by the phase modulation. And this is another type of spiking behavior that we observed by varying the input pulse by some time of intervals. So the spiking, bursting spiking behavior means that it will have a group of spiking, though it's not identical. The next spiking is non-identical over the time period. So this is also done by both the modulating the phase and amplitude so far. And to make it more uh, variable or more dynamic, we are required to do some more analysis on these things also. And if we come to the conclusion, so far we have presented the anisotropic gradient that we engineered in a 200 nanometer nanotrack to drive the AFM Skyrmion. And then we also have seen the LIF neuronal functionality, how it works in our case, and also we have observed different kinds of spiking modes based on their spiking patterns, which one is fast, phasic, and bursting. And our future work plan, that as we are in initial position of that work, we are more working on the control circuit, that we are considering the input pulse, the type of input pulse, the modulation that we are considering, how it can be achieved by additional control circuit. And also, right now we are considering the uh, rectangular nanotrack device. We will also consider few other type of nanotrack like trapezoidal. And also we would like to more investigate on the reconfigurability aspect, that how it can mimic exactly the same without uh, adding any other circuit with the same device. How can we can mimic the same things? I think this is from our side. So if there is any question,
Thank you for
thank you
interacting.
for all.